Principles of Control video. Introduction. Today we're going to be outlining the nutrient control program and some principles of control and how they're used in the greenhouse. Areas we're going to cover today include principles of control, including feed-forward control, proportional response, integral response, and a combination of feed-forward and proportional integral response, and a summary. Principles of control. Principles of control outlines how the Argus control system calculates on the fly the amount of concentrate to administer and the self-correcting strategies that are used. Although the control settings that govern these functions are normally set up and adjusted by Argus, it's useful to understand how your control system manages your multi-feed equipment. Feed-forward control. Key concept. Using the system flow sensor, calibrated injectors, and the declared concentrate strengths, the Argus system predictively calculates how much concentrate to add to achieve the current target. Feed-forward control is based on predictability and repeatability. To the extent that the final electrical conductivity, EC, or pH of a given dilution can be reliably predicted, you can use predictive calculations to determine how much concentrate to add to the water stream at any flow rate. For example, if we know that a 200 times dilution results in an EC of 1.8 millisiemens, the system calculates that it must add 1 part of concentrate for every 199 parts of water to achieve this EC. Since EC varies indirectly with concentration at horticultural concentrations, the system can also predict that 1 part concentrate in 399 parts of water, or 400 times dilution, produces an EC of 0.9 millisiemens. There are several advantages of predictive feed-forward control over closed-loop feedback control. These include fast response. The system does not need to wait for a deviation from the target to respond. Reduced oscillation and process lag compared to feedback system. Safety. Maximum dosing limits can be specified. Flow must be measured in the system before chemicals can be administered. The accuracy of predictive feed-forward control depends on the accuracy of the input values that are used in the calculations. Garbage in equals garbage out. The Argus system calculates feed-forward output values using the following input information: the current irrigation system flow rate from the flow meter, the calibrated stock solution flow rate across the metering injection valves, the declared strength of your stock solutions. If all these inputs are accurate, the control results are an accurately diluted feed. In practice, there are many sources of error that can cause the predictive calculations to be slightly off, even when great care is taken in calibrating the system. However, this is not a problem so long as the predictive settings are producing a result that's close to the target. With fine-tuning of the input values, such as the declared feed strengths, you can achieve highly accurate dosing using only a feed-forward strategy. The Argus system provides methods for automatically adjusting small errors in the feed-forward output values by applying closed-loop proportional, integral feedback correction to any deviations occurring between the measured EC or pH results and the targets. By using a combination of feed-forward predictive control with feedback correction, the system achieves safer results that are more responsive and more accurate than when either of these strategies is used alone. The next sections of the video explain how Argus uses proportional and integral tuning methods to accomplish feed-forward with feedback correction. Proportional response in controlled systems. Key concept. A proportional response is varied directly with the instantaneous direction and magnitude of a measured deviation from the target. A proportional response calculation is commonly used in feedback-controlled systems. With proportional control, an instantaneous output value is calculated in response to the degree to which a measured variable has deviated from the target. It's important to note that proportional control is not concerned with how long a deviation has occurred, only the size of the deviation. A small deviation produces a small output response, and a large deviation produces a larger output response. In this example, as the measured EC, or the red line, deviates from the target, the green line, the control system applies a proportion corrective output response, the blue line. The span, or P band, over which the output is proportioned is 10 millisiemens. Therefore, the output, or the blue line, increases evenly from 0 to 100% as the deviation, or the red line, increases from 0 to 10 millisiemens. Notice also that at the end of the displayed time span, the EC is still slightly deviating from the target and the output is producing a steady response. This is a common phenomenon when using a proportional control strategy by itself. The system has become balanced just below the target with a steady corrective output. Since the measured deviation is not increasing or decreasing, the output remains steady. Proportional control alone has no mechanism to correct for this residual error, it can only respond to it. If the deviated value is not changing, there is no way to increase or decrease the output to drive the measured value back to the target. To correct for this situation, we can introduce a second concept called an integral control strategy that is applied together with proportional control. This combined approach is often referred to as PI control. Integral response in controlled systems. Key concept. An integral response varies with the direction and the length of time of a measured deviation from its target. An integral control strategy is often used in conjunction with a proportional control strategy. Integral control considers the length of time that a deviation from the target has occurred and produces a control response in proportion to the amount of time that's elapsed. An integral calculation is not concerned with the size of the deviation, only with the duration. The integral calculation does not care about the amount of the actual deviation. In this example, the integral controller notices that the measured deviation, or the red line, is below the target, the green line, and gradually ramps up the integral output response over time, the blue line. This ramp continues to increase even when the measured deviation begins to shrink. When the deviation crosses the target and becomes positive, the integral controller begins reducing its output value. In this example, the deviation drops back down below the target, so the I value begins climbing once again. The desired output value continues to climb at a steady rate even though the deviation amount is less than the first interval. Eventually, if the deviation is not returned to zero, the output reaches its maximum output value. While integral control can be used by itself in some circumstances, it's usually used as a means of correcting for the offset phenomenon that commonly occurs when using proportional control. Should an offset or steady state condition occur with proportional control, the integral timer increases the output over time to correct it. Whenever integral control is used in conjunction with a proportional control strategy, it's referred to as PI control, proportional integral. When properly tuned, a PI strategy can react quite well to sudden changes, P, and still achieve longer-term average target values, I. Using a combination of feed-forward and proportional integral response and control system. Argus often uses a combination of feed-forward and proportional integral PI feedback control strategies. This integrated approach helps to overcome the inherent problems possible if either strategy is used alone. Open-loop strategies that use feed-forward calculations are only as accurate as their calibrated information. Even when great care is taken with the settings, there's likely to be a slight difference between the target values and the measured results, or the readings. Since feed-forward calculations do not contain any self-correcting capabilities, offsets tend to be steady. Feedback control also has its drawbacks. It depends on the sensors that directly measure the process, such as EC and pH, and temperature sensors. Throughout the controlled system, there are several process lags, making it impossible to instantly react to deviations between the targets and the readings. These lags mean that the controlling environment equipment is always a bit behind the actual events when it applies its corrections. It's chasing a moving target. Whenever you rely exclusively on feedback control, there's a tendency to produce cyclical oscillations as the controlled equipment first undershoots and then overshoots the targets due to process lag. To some extent, these oscillations can be tuned out by using proportional and integral feedback control settings that match the process, but this can be a very difficult proposition and may require frequent retuning as external conditions change. Not very satisfactory for everyday control. An integrated strategy using feed-forward control with feedback correction can produce very accurate and reliable results. The feed-forward calculations do the bulk of the work and do it with no process lag, usually getting the reading to within a few percentage points of the target. The feedback correction program measures the residual deviations, makes the feedback corrections, and adjusts the control system response to drive the reading closer to the target. This diagram shows how feed-forward and feedback correction strategies work together to achieve the target. The feed-forward calculations produce an output value, the blue line, resulting in a reading slightly below the target. This small offset is then automatically corrected by the feedback control settings. It increases the output response, or the blue line, until the reading matches the target. For a more in-depth look at using principles of control programs, check out the next video in the series, Using the Nutrient Control System. Click the link below to open the new video. For more information on nutrient systems, see the hydroponic nutrients and multiplexing irrigation and nutrient control system videos, the Multi-Feed RM Operator Guide, Nutrient Control Systems Reference Manual, Nutrient Dosing Handbook, or contact Argus support.